These are the things that we have learned for this chapter, okay? And then we will continue with that. So under chemical equilibrium, okay, we have learned about reversible reactions. So what are reversible reactions? Reversible reactions are any reactions that can proceed in both forward and backward. Example, if you have nitrogen reacting with hydrogen, okay, in Haber process, this is going to be one example of a reversible reaction. So for any reversible reactions, okay, they will react and they will reach equilibrium. Equilibrium is going to be a state where they are going to be stable. It means there's going to be a stable situation where the reaction is still going to be reacting. Okay, the product and reactants are still going to be there. Okay, they are continuously reacting and so on. So therefore, okay, we say that okay, the reaction continuously happening, but they will reach a state where they are in equilibrium. So what are the points that we need to remember under equilibrium? When we say that this particular reaction has reached equilibrium, or when we say that, okay, this production of ammonia, this equation that we mentioned over here, once they have reached equilibrium, what are the criteria that they must have? So maybe you guys can actually tell me, Ashley, we have 4 points under equilibrium. What are those?
Um, Forward reaction must be equal to backward rate of reaction.
Okay, rate of forward reaction must be the same or equal. Okay, rate of forward reaction must be equals to rate of backward reaction. And what else, Davis?
Dynamic.
Okay, the reaction must be dynamic. Can you actually explain to us what is meant by dynamic?
Like change.
Not change, it's actually dynamic means the reaction continuously to happen. The reaction don't stop. Okay, so it means the conversion of nitrogen and hydrogen to become ammonia, and the conversion of ammonia to become hydrogen and nitrogen is going to be happening continuously. If you leave this reaction, let's say when you mix N2 and H2 to give you ammonia, and let's say the world ended, and even after 3,000 years you come back, okay, they are still going to be reacting. It means hydrogen, nitrogen, they are continuously being changed into ammonia. Ammonia is changing into nitrogen to hydrogen. They don't stop. Okay, this is in assumption that it is in a container. So when they are in container, Lindsay, we call it what system? Is it open system or closed system? Yes, so they must be in a closed system. So the reaction is dynamic, okay, because they are in closed system. And therefore, since the rate of forward and rate of backward is the same and is dynamic and it is closed, nothing goes in, nothing goes out. So therefore, what can you say about the concentration, Kendra? Concentration of, let's say, reactant and product at equilibrium. What can you say?
The when if the time longer, the reactant become more.
Basically, you don't revise, Kendra. Okay, there are 4 things that you need to actually know about this. Okay, so this one, okay, the concentration must be constant. So the concentration, once it reach equilibrium, okay, once it reach equilibrium, they are going to maintain the same concentration. Same doesn't mean they are the actual value is same, like concentration of nitrogen, hydrogen, and ammonia going to be the same. No, that doesn't mean that. It means, let's say the concentration of nitrogen is 1. Maybe the concentration of hydrogen is 2. Maybe the concentration of ammonia is 3. They remain 1, 2, and 3 throughout, even let's say after 3,000 years. Yeah, they are going to be the same concentration. The concentration will not change. So this is after they have reached equilibrium. Okay, so here, okay, there is another principle over here. When it comes to equilibrium, we call it equilibrium principle. This was discovered by this principle was actually proposed by a French chemist. Okay, his name, okay, CHATELIER'S principle. Okay, so how do you pronounce this? I think in Singapore we actually I think even if you can actually relate this to Indonesia, the way we that can help you to pronounce is like something like a Chinese name. How? Okay, normally if you have, this is Li, okay, it's Li. So you just remove one of the E, is Le, okay, Le. So this one Chinese name Chat, Le Chat, okay, Lie. Okay, this is how Singaporeans we memorize. Yeah, how do we pronounce Le Chat Lie, Le Chat Lie's principle. So if you are wondering how to pronounce it properly, yeah, you can actually use that, Le Chatelier's principle. This principle states that, okay, whenever a system in equilibrium, it means satisfying all the four things that I have mentioned just now. When they have satisfied that, it means they are in equilibrium. The moment you make some changes to that equilibrium, the changes can come in many ways. The changes can be changes in concentration, changes in temperature, changes in pressure. When you do some kind of changes, okay, there will be the system itself. Okay, the system itself will try to overcome those changes. Okay, it will try to eliminate those changes. So the system will change the position of the equilibrium. Okay, the system will change the position of the equilibrium to overcome the change. That is actually what is meant by Le Chatelier's principle. Okay, they say that when you actually do something, this principle say that the system will try to eliminate the change. How to eliminate the change? Then they will play around with the position of the equilibrium. The position can be either move towards forward, or we say right hand direction, or it can actually move backwards. We say left side of the reaction. It means it will move to the left. Okay, so this one you need to actually learn how to apply this. Okay, but if you look at this graph, I'm going to actually show you this representation using graph first. Let's actually look at change in concentration. Whenever I write like this, okay, you should understand by now, okay, this is concentration. Okay, concentration. So let's say if I actually try to demonstrate related to concentration, but let's draw, okay, when I have, let's say, A plus B to give you C, it means 1 mole of A react with 1 mole of B to give you C, for example. And let's say A and B, I think everyone knows that A and B, they are reactant. Okay, C is the product. So normally reactant, they will actually start with a particular concentration. Okay, so let's say I'm going to, in this thing, I'm going to actually show for A. Okay, A is going to be the reactant. I will only choose one. Okay, A. And I'm going to choose C as the product. So if I'm going to show that, okay, let's say I'm going to use this purple ink or pink ink. So here, when you have this A at the beginning, when time equals to 0, there is a concentration of A. And as time proceeds, okay, the reaction will continue until they reach equilibrium. Let's say I'm going to actually take this time as the time where it reaches equilibrium. Okay, so just to make it easier to see, I'm going to actually put a dotted line. Okay, assume that this is the time where they reach equilibrium. It means they are reacting. Okay, now when A reacts, Jordan, the concentration will decrease or increase.
If what, sir?
If A reacts to give you A plus B to give you C, will the concentration decrease or increase?
The concentration of A.
Yeah.
If it reacts, it decreases.
Okay, if it is reacts, it decreases. The same applies for B. Okay, but I'm showing for A. So they are going to decrease, and I will actually draw a curve. Okay, it's decreasing. Now, once it decreases, the moment when they actually reach equilibrium, what can you say about the concentration at equilibrium, Josh? The concentration is supposed to be constant. Okay, the concentration should be constant. It means that, okay, the concentration is constant means, okay, the graph will be something like this. From this moment, it's going to be a straight line. It's a constant concentration here. Now, let's say I want to actually draw, okay, another graph, okay, to show related to my product C. Okay, Justin, at the beginning, when you actually react something, do you have product, Justin?
When you react A and B, of course you have C. Yeah, it's a product. You have reactants, you have products.
No.
What do you
At
mean?
the beginning, when time equals to 0, do you think you have product?
No. Don't have time to react. Yeah, don't have.
Okay, 0, right?
Yeah.
Okay, it is 0. Now we know that, okay, when it is reacting, there is going to be some kind of a, let's say, in this case, the concentration will increase because it's a product being formed. Okay. Now, when you see the number of moles is 1 mole, 1 mole, and 1 mole. If let's say, if I replace this from here to here, from here to here, if I measure, let's say this one is about maybe close to 1.5 centimeter. Okay, according to my screen on my laptop. Yeah. So let's say that is the length, okay, of decrease. If that is the length of decrease, if I am actually forming the product, you're supposed to actually follow the same length of the increase, because 1 mole is reacting, then 1 mole is being formed. Okay. So how am I going to sketch the graph? Roughly imagine, yeah, let's say from here to here is also the same length. The same length x, same length x over here. So it means that when I draw, okay, I will draw something like this. The concentration will increase maybe up to here, maybe up to there. And once it reach equilibrium, they start to actually become constant. Can you understand this? Okay. Now, imagine now I'm trying to actually draw the same graph, but I'm going to actually change that equation to become A plus B to give you 2C. And let's say I'm going to still use, okay, for A. I want to actually show for A. And I'm just going to use the same thing, let's say about 1.5, yeah, 1.5 according to my screen. So roughly it's going to be, let's say this is still my equilibrium point, okay. So it decreased up to here, then it became constant. Okay, that's the concentration, yeah. Concentration of what? Concentration of A. Now, I know this is going to be X, the length, yeah. Now, I want to actually show that, okay, to my C. But take note that every 1 mole will give you 2 moles of C. It means every that X change, you are going to get, if this is X, you are going to get, this is decreased by X. Okay, this is decreased by X. You are going to also have decreased by X. 1 mole will react with 1 mole. But how many X you will get for C, Jennifer? Just try how many X. Kenneth, I cannot see you. So maybe Cleanta, you can help me. If there is a decrease by X unit, how many increase you expect for C? Yeah, double. Increase by 2 times because of the 112, similar to what we have learned with stoichiometric equation. So it means that if you have X, earlier C.
So I have a question. How do you
Not clear, Kenneth. Okay, let him recover from that. Kenneth, not clear?
So I have a question.
Yeah.
How do you find like the concentration? Like, how do you like find the concentration? Like, how do you know it's X?
Because I'm drawing. Okay, it means whatever things that I'm drawing,
just like an
I'm
example.
taking it. Yeah, I'm taking it as trying to draw using the same scale. Yeah. So I'm trying to actually just demonstrate to you. Okay, for that decrease, your product will also increase by that much. Okay, basically how you estimate. Okay, from here to here is this much. Okay, then I'm going to estimate that is going to be the same increase that I'm going to have. Okay, so something like that. So here, like for example, if this is X, okay, you measure, yeah, roughly this is going to be, let's say, the changes that is happening. Now, I know the C is supposed to increase by how many? Let's say from here to here is about 1 cm. I expect the changes will be 2 cm, 1 cm, 2 cm. You can see this is 1 cm, this is 2 cm. So I am expecting, okay, the blue line supposed to increase all the way up until here. Okay, all the way up until there. And then they are going to actually become equilibrium. You can see roughly, depending on the equation, the way they change is different. Now, what I want to teach you now is, okay, what happens when you are already reached equilibrium. This is actually what, once you actually reach equilibrium. Okay, this is equilibrium. Once you reach equilibrium, let's say I am going to make some changes. Okay, I'm going to make some changes at certain time. How? Let's say I am going to actually increase the concentration of A. It means this was a closed system, but now I'm going to actually increase the concentration of A. Now, just to be easier to see, this is A, this is C. This was A, this is C. Now, if I want to increase the concentration and make it double, okay, at this particular time, for example, I say at this particular time, I want to increase the concentration of A and make it double. How to make it double? Okay, imagine here, this is going to be the initial concentration, this length. How to make it double? Immediately you are adding the A. It means the graph immediately goes up with this unit. So it means it become, let's say this is X, this is going to be roughly X to become like this. It means the graph suddenly changed to this. It's a straight line up. Okay, let me draw again, yeah. So basically I'm increasing the concentration. Okay, I'm going to erase this part first so that easier for you to see. It means I am actually adding A suddenly. Basically, I am disturbing the equilibrium. Okay, I'm disturbing the equilibrium. According to LCP, let's actually look at this equation first. Okay, let's say now, okay, when I increase the concentration of A, Josh, what will happen if I increase the concentration of A according to LCP? What should
More C, more
it
C will
means,
be produced.
it means you need to actually eliminate the change. What is the how do you eliminate the change? Basically, you try to remove the extra A. Okay, you must try to remove the extra A, so the position will shift to the
right.
Okay, when the position is shifted to the right, what will happen? Your A will become decreased. Okay, because you're using the A. At the same time, because it's going to the right, B will become decreased, and C is going to be increased, the concentration. So let's see whether we can actually show that, okay, in this particular graph. Now, when you decrease the concentration of A, you cannot decrease to the original condition. It means, okay, let's say this is going to be a new equilibrium going to be formed over here. A new equilibrium is going to be formed here. When I decrease the concentration of A, this is A, it don't actually come back to the original position earlier before the change. It will never happen. Okay, it will never happen. You can only decrease to certain extent. Okay, so the more logical term will be maybe it decreased to become like here. Okay, it decreased slightly only. Okay, now it is very important to take note of this. They will become constant now. So now imagine the changes that is happening over here. It's about 1 centimeter. Okay, please take note. The changes is roughly, let's say, 1 centimeter. So what will happen to the blue line? Okay, the blue line is C. Every 1 mole change will give you 1 mole change over here. Every minus X, you will gain X. So it means this is going to be minus X. What you're supposed to get, the blue line will actually gain, okay, roughly the same length from here to here. So let's actually I guess, yeah, roughly 1 cm. This is going to be roughly 1 cm. Okay, or you want it to be slightly higher. This is going to be from here to here. Means basically this length and this length, they are the same. I hope you understand. Okay, so if I erase this, it means that, okay, the idea is this blue line, they start to increase up to here. Okay, let me draw nicely. They increase up to here. I erase this part, and they start to re-establish a new equilibrium. This is new equilibrium. Nevan, can you understand this?
Yes, sir.
Okay, so basically we are using the length, yeah, the height. Okay, why I'm showing you this, because I want you to also understand using graphical form. Okay, questions can come in the graphical form also. Okay, so please take note. So let's say now I represent this using a different equation. Okay, using different equation. And now let's actually try something else. Okay, let's try some other changes. Earlier, what I did, I increased the concentration of A. Let's actually try to increase the concentration of C. Okay, let's increase the concentration of C. Okay, let me erase all this part first, so that easier to see. Let's say I'm going to actually decrease the concentration of C, the blue line. So I'll actually follow the blue line. Let's say everything is going to happen here. So what I'm going to do, I'm going to erase the line. So I just put, okay, it was until here. This is already equilibrium, yeah. So I'll write down, this is equilibrium. Okay, now what is happening? I'm trying to increase the C. Okay, I'm actually trying to increase the C. So let's say what happens according to the equation, yeah, when you increase the C, okay. So Annabelle, what will happen when you increase the C according to Le Chatelier's principle?
The A and B decrease.
No? When you actually have increase in C, you need to actually eliminate the change. It means you need to remove the C. How do you remove the C? By making C to react to give you A and B. Okay, that is the only way how to decrease the C. Okay, the position of the equilibrium will move to the left. So in that process, what will happen? In that process, the C will become lesser, not really less to the original position. Okay, it will become lesser. At the same time, A will increase, B will increase. Let's actually try to show that here. So I am increasing C, for example. This is blue line is C, so I'm just showing blue line. So here, let's say I'm increasing up to here, to here. Let me erase this. Okay, I'm increasing this much. Okay, so let's say I'm just draw here. I say I indicate, okay, this is X. Okay, increase by X. Now, when there is increase by X, what is going to be happening when there is a change of X? Okay, because do remember, if this one, I think better not to say plus X. I'll just put when there is X over there. What do you expect the changes when it comes to A? You see 1 mole, 1 mole, and 2 moles. So Jordan, when it comes to A, what do you expect? Is it 2x or half X?
Half.
Yes, it will become half X. So it means the changes that we are expecting, okay, from A is only half of that change. It means if I actually draw using the pink over here, I know that A will, okay, A, what will happen to A? A will increase. Increase by how many? Increase by half of this length. So maybe up to here, okay, up to here, but it will not increase directly up, okay, because they need to re-establish the equilibrium. It will take time. It's not sudden increase, yeah, like what we did for the, because C means we change it intentionally. Then the system will take its time to rearrange. So let's say I'm supposed to reach somewhere half to the X. So probably I need to increase up to here. So what I do is the graph will increase. And then they will become constant. And what will happen to this blue C, yeah? Okay, what will happen to C? C is supposed to decrease, but not completely. Okay, like for example, if this one is, imagine if this one you take it as X, okay, they must decrease double, yeah? So maybe I will decrease up to here. So this one, the graph will decrease more compared to the increase by A. Okay, so they will start to reach over here. Take note, the line, this line is not the same as this line anymore. Okay, it's not the same, it's slightly higher. Okay, slightly higher. So what we can say about this graph, this is your new equilibrium. This is what happens. Okay, this is happens when it comes to, okay, changes in concentration. Okay, we can show that in terms of graphs. Okay, so equilibrium and new equilibrium will be formed. Okay, so now what I am going to teach you now is, okay, please take note. Yesterday, what we have learned about concentration, I have extended that knowledge when it comes to showing it using the graph. Okay, they have mentioned it in the textbook, but they only show some graph, okay, only 2 graphs, related to hydrogen iodide, but they didn't discuss in detail over there. Okay, so you need to you need to actually go through these notes. Okay, I will actually try to upload these notes. Okay, maybe this video you can actually go through that again. Okay, because it is very important to understand this, because in different syllabus, okay, they actually ask you to sketch the graph, and I don't see any reason why they cannot ask you to sketch the graph. It is possible. Okay, it is possible. So if I happen to see any questions related to that in the past year paper or something, maybe I'll be the first person to actually expose you to those questions. Yeah. So, but please take note. Okay, it's definitely possible, and I have seen this type of question in other syllabus. Okay, Singapore syllabus. Okay, some other Cambridge syllabus, we call it EdXL. Okay, they actually went into this method of asking questions. Okay, sketching and explaining. Yeah, so maybe for our syllabus, not many questions on this. Okay, but anyway, I will actually teach you now related to how do we use the Le Chatelier's principle. Okay, when it comes to changes in temperature. Earlier we did the related to changes in concentration. So let's actually look at changes in temperature. Now, this is an extension to what I taught you, okay, in enthalpy. I told you to remember related to the hand, right? So this is the time that you apply the hand concept. Now, imagine I'm going to actually draw the hand, okay, this is my hand around this equation. Okay, around this equation, that is positive 9.6. Okay, Angela, your hand will feel hot or cold?
Cold.
Okay, this is going to be cold. Good. Okay, if this is cold, automatically you put another hand over here. If that is cold, of course, here is hot. Okay, so you need to actually identify that first. Now, if let's say this system is already at equilibrium and I am increasing the temperature. Okay, I'm increasing the temperature. Now, according to Le Chatelier's principle, okay, when you increase the temperature, what you need to do? Josh?
For increasing the temperature, so
I need
on
to
the
decrease the temperature, right? Eliminate the change. So temperature goes up, you need to decrease the temperature. Now, can you suggest to me, Josh, how do you decrease the temperature using the hand situation that I put over here? Do you think that cold will become hot or hot to become cold? How do you decrease temperature?
hot to become cold.
Yes. So this will help you to tell you the position of the equilibrium is now is going to be shifted to the right. Okay, please remember this. So when you increase the temperature, what will happen? The position of the equilibrium, okay, position of equilibrium will be shifted to the right. Okay, shifted to the right. When it is shifted to the right, okay, what do we expect? Okay, we will expect more concentration of H2. We expect more concentration of I2, and we expect the HI to become less. This is what we expect. Do we write this in your exam? Now, when you write this in your exam, okay, I want you to add another one more term. What is the another term that I'm actually going to suggest you to write? Because based on the past year papers marking scheme, whenever it is involving temperature, they don't want you to say position shifted to the left or to the right. What they want to see is the position of the equilibrium is shifted towards endothermic or exothermic. So in this case, going to the right, okay, going to the right, Kiara, is it going to be endothermic or exothermic? This is positive. Going to the right means endo or exo?
Endothermic.
Yes. So instead of writing position of the equilibrium shifted to the right, this is actually your thinking process. I will suggest, okay, this one you leave it up to your thinking only. Yeah. Make sure that, okay, when you write your answer, instead of that, doing position shifted to the right, you just say, okay, the position, okay, the position of the equilibrium. Okay, the position of the equilibrium shifted to favor, okay, shifted to favor endothermic reaction. Why I'm teaching you this? Because I want your answer to be the same as the marking key. Okay, so position of the equilibrium, yes, it is universal for all. Okay, but when it comes to temperature, I would like you to actually write down in terms of shifted in favor of what? Endothermic or exothermic. Okay, in this case, it is going to the right, so it favors endothermic reaction. But let's say in other questions, suddenly it moves to the left. Okay, and we know that this is positive, is endothermic. Moving to the left, it will favor the exothermic reaction. So you need to actually mention that. Okay, so that is going to be one of the way. How do you actually mention about the changes of temperature? So here, that is going to be an endothermic reaction. Let's actually have a look at exothermic reaction. One example. Okay, so the first thing that you need to do is to draw a hand over here. Okay, so Dylan, what is this? Hot or cold?
Hot.
Hot. So automatically another hand will appear here. This is cold. Let's say earlier I mentioned that I'm going to increase the temperature, but now let's say I'm going to decrease the temperature. Okay, according to the LCP, Chatelier's principle. Okay, when you decrease the temperature, you need to make sure that you try to increase the temperature. How do you increase the temperature, Justin? Cold to hot or hot to cold? Yes, so the position of the equilibrium is shifted to the right, but I want you to keep that in your thinking process only. But when you write down the answer, you just write down the position of the equilibrium. Okay, the position of the equilibrium is shifted to favor what? Klienta. Moving to the right. What is this? Endo or exothermic? Ella, you want to help? Endo or exo? Okay, so this is going to be exo. So it means the position of the equilibrium is shifted to favor exothermic reaction. So if it is happening, so what do we see? Okay, we see that N2, okay, the concentration will decrease. The concentration of H2 will decrease. And you will see the concentration of ammonia to become more. Okay, these are the things that will happen according to the principle that is mentioned. Okay, you need to know both. Okay, how to apply. Okay, that is going to be related to temperature. So let's actually go for the another one. Changes when it comes to pressure. Okay, changes when it comes to pressure. Now, when it comes to these changes related to pressure, I can actually use the same example like just now. N2 gas, okay, plus 3H2 gas to give you 2NH3, also gas. Now, do remember, okay, your changes in pressure affects only gaseous particles or gaseous molecule. Okay, only gaseous molecule. So those who are not, which are not gases, we will actually ignore them. Okay, how do we ignore? So there is a trick over here, something similar to the temperature. So you just look at the number of moles. This is 1, this is 3. Number of moles of the reactant, 1 plus 3. Total, you just put 4. Put a circle. What is going to be the total number of moles at the product? 2. Okay, put a circle. Now, when I increase pressure, okay, when pressure is increased, what will happen here? Let me actually use the theory. Okay, when the pressure is increased, according to CHATELIER'S principle, okay, they say that I need to decrease the pressure. Okay, how do I decrease pressure? I decrease the pressure by having less number of particles. If you have more particles will hit the wall of the container, and then you will have more pressure. So if I increase the pressure, I need to decrease the pressure. How do I decrease the pressure? By favoring the reaction that makes my pressure low. How to favor the reaction that makes the pressure low? By favoring it towards something that can give me less number of particles. In this case, I will move from 4 to give me 2 to form less. Okay, to form less. So the position of the equilibrium is shifted to the right in this case. Okay, so what do I write over there? Okay, when the pressure is increased, okay, the position of the equilibrium, okay, the position of equilibrium is shifted to the right. Okay, is shifted to the right to favor less number of particles. Therefore, what will happen? The concentration of N2 will decrease, concentration of H2 will decrease, concentration of ammonia will increase. Now, maybe some of you still confused. Let's actually look at diagram. Okay, let's look at diagram so that you can understand things much more better. Okay, when you look at this diagram, you can see there are certain number of things over there. Let's say this is the equation. Okay, the purple plus yellow. Okay, it's a reversible reaction to give you yellow and the purple. Yep, those are the particles involved. So let's actually count in the beginning. Okay, in the beginning, how many particles that we have? I have 1, I have 2, I have 3, I have 4, 5, 6, 7. Okay, assume that molecule is going to be 1. Yes, 7 particles over there. I put 7 over here. Now, when the pressure, okay, when the pressure is increased, you see here, how many particles here? 1, according to the equation, 1 and 1. So this is 2. This is 1. Can you see? Okay, number of particles. So when I increase pressure, okay, when I increase pressure, I need to favor something that has less. It means I need to have less pressure. It means favor something that has less molecules. So the position will move to the right. Now, how do I represent this over here in diagram? When the pressure is increased, it means I am actually going to show the pressure is increased by reducing the volume. The volume becomes smaller. So it means pressure is increased. Now, when that happens, what will happen is you are going to form more of this molecule. So you can see this and this, they will come and join this. This is the earlier one, so they remain. Maybe this and this, they come and join this. And this one, they didn't react. They just want to be alone. So they be alone. So the total number of particles that we have over here is actually 5. And you can see, okay, and you can see how the position is shifted. You can see the pressure. When the pressure is increased, you are going to form from 7 to become 5. It means you are trying to reduce the number of molecules so that the pressure that is exerted by the system is kind of going to become lesser. So that is actually explained about how do we apply this situation for that. Okay, so if you still don't understand, okay, let's say if I try to represent using another equation, yeah. So let's say, for example, H2 plus I2 to give me HI, and all of them are gas, and this is going to be gas. Now, if you look at the total number of moles, okay, of this system, okay, 1 plus 1, so total 2. And if you look at this is going to be 2. I just want to ask you a simple question over here. When the pressure is increased, Lindsay, do you think the position of the equilibrium will change?
It will not shift, right? Because it has the number of moles.
Because okay, the number of moles are the same, so pressure do not have any effect for this case. But if I have another situation, of course, I don't have a proper example to show you, but I'll show you using A, B, and so on. Yeah. Okay. If this one is going to be 2C and gas. Now, do remember, it is only affecting gases only. Yeah. So you can see that what is the total number of moles on the reactant part. So Dylan, what is total number of moles of the reactant?
2.
Normally we select 2, but now in this case, it's going to be 1. Why? Because A is solid. I will ignore the solid. So I will only consider B. And then what is the overall for the right-hand side? The product is 2. So let's say if I decrease the pressure, according to LCP, I need to actually increase the pressure. How do I increase the pressure? I will shift the position of my equilibrium to the right to form more number of molecules. So this is how you apply. Can you understand, Dylan?
Yes.
Okay, let's actually go for the last one. Okay, the last one is going to be, the question is, we have learned about concentration. We have learned about pressure. We have learned about temperature. The question now is, can catalyst affect position of the equilibrium? The answer is no. Okay, catalyst functions to increase the rate of reaction. How? By decreasing the activation energy. Now, if let's say I have A plus B to give you C, and I use catalyst, does it mean only the forward reaction is speed up? Ashley, if I use catalyst, what can you say? Because in a reversible reaction, there are 2 types of reaction, right? Forward and reverse. Do you think the catalyst only speed up the forward reaction, or does it speed up both, Ashley?
Both.
Yes, catalyst speed up both of the reaction. Okay, forward and reverse. Because of that, they do not have any effect towards position of the equilibrium. If they actually speed up only one particular direction, then of course the position of the equilibrium will change. Okay, so this is going to be an application also. Okay, catalysts speed up both reactions, forward and reverse. Therefore, they do not affect the position of the equilibrium. That's it, actually. Actually, I wanted to teach you more on this, but this one can wait tomorrow. Yeah. So this one, okay, what we have learned today. Yeah. So I want someone to actually summarize what we have learned today. Michelle, can you actually summarize what we have learned today?